Thank you for that introduction, Mike, and thanks everyone for joining this discussion today. I'm going to present modern attacks and some advanced strategies to address the modern attacks. Today we are going to cover some of the modern attacks that we have seen in the past few years, and some of advanced strategies that we can use to actually defend against such type of attacks. Today, we're going to cover supply chain attacks. We're going to cover vulnerability exploitation, credential theft, ransomware attacks, 5G, IoT type of attacks that are relatively new technologies that have been deployed quite heavily in this kind of nascent industry, and we're going to cover some of those 5G IoT based attacks as well. So with that. We're going to cover the supply chain attacks. There are two types of supply chain attacks that we're going to cover today. There's hardware-based supply chain attacks, and there's going to be software-based supply chain attacks. In the hardware-based supply chain attacks, typically the customers order hardware products from any vendor manufacturer to be deployed within their infrastructure, within their IT environment. So what the attacker would try to do in this particular case is they're going to intercept the shipment while the product is being shipped from the manufacturer to the customer. They're going to open the box and they're going to power up the device or the appliance. Typically, like these appliances have default passwords. They're going to log in using the default password, and once they are logged into the system, they're going to try and replace the operating system, or they're going to replace the software with their own malicious software. They're going to embed their own malicious piece of software. If they don't replace the entire operating system, they may end up planting some malicious code within the operating system. And once they actually they put in their own Trojan or rootkit or whatever they want to put in on the system, they're going to repackage the system within the original packaging and make it look as if it was never being tampered with, and then they are going to put that drop that shipment back in the mail. So when the customer receives that piece of hardware, or the appliance, they would actually take that product and deploy it within the infrastructure. But then, the software within that appliance would have been already tampered with, and depending on what kind of malware or what kind of malicious software that the attacker has put in, typically they would actually have remote command and control access. That's the most preferred method, where people would actually try to get remote access into the system and try to issue commands to that software so that it can go perform other tasks within that environment. In some cases, that may not be possible, and they may actually doing more snooping or reconnaissance, where the software is passively listening to various types of communication that's going on within that particular infrastructure, and then periodically phone home all of the events that are happening, that they capture some crucial data from there. So this is actually a typical supply chain attack that we have seen in the recent past. So we're going to cover some of the defense mechanisms that we can actually use to mitigate these kind of hardware supply chain attacks. So one of the things that comes to mind, the first layer of defense would be a secure boot, where we can actually ensure that the software that is running on any system is indeed trusted. Right, and the trust actually is established, when there is actually a trusted, root anchor within the system, that actually is the root of trust. So if that root of trust is anchored on the hardware that is burnt into some piece of hardware on the system, that is more secure, because it's harder to tinker with hardware. Where if it's actually embedded in a chip that's burnt onto the board, it would be very difficult for the attacker to solder out the hardware and then put in some new chip. But if it is actually a software-based root of trust, then it's going to be more easier for the attacker to tamper with. So within the software anchored root of trust, potentially the firmware would actually be prone to like more attacks where when we try to establish a root of trust, there'll be a trusted CA certificate or X.5 certificate that is the primary root of trust, which then authenticates the BIOS, and the BIOS would then authenticate the bootloaders, and the bootloaders would then authenticate the kernel, and the kernel would then authenticate the actual operating system, right? But if the root of trust is not anchored within the hardware, then that software anchored root of trust can be tampered with. So the attacker can potentially replace the certificate that is used to verify the software root of trust, and they can actually like replace the firmware or and such kind of attacks are possible. So to harden against those kind of like software-based, root of trust, because hardware-based anchoring of root of trust is more difficult to achieve with the manufacturing process, and the software-based, anchoring is actually more, achievable. Is less complex to achieve. It's more popular, but then it's more prone to more attacks, right? So if we choose like software anchored root of trust, then we can actually do like additional layer of hardening by actually pinning the certificate that is used to verify the root of trust, and that certificate itself can be like embedded within a hardware TPM if it is available, or if it's a more virtualized environment or a public cloud environment. These virtualized environments provide a virtual trusted platform module in which the certificate can be pinned, right? And another form of like hardening, it would be the measured boot using the TPM, where we actually like can harden the whole boot sequence, by measuring the boot, and that would actually like harden the entire like secure boot process, and provide an operating environment where the operating system itself can be trusted, right? So that is the first layer of defense. Now, if we are actually like trusting the operating system itself, that by itself may not be sufficient, right? Because if the attacker knows that the operating system is being protected using a secure boot mechanism, they may not want to tamper with the operating system, but instead they may actually want to plant their own like software, embedded there, or hide their own Trojan within the operating system. So in that case, how do you defend against that kind of attack, right? So that's where we can consider what's called a verified execution, where we built a custom kernel within that operating system, where if any executable is about to be executed on that particular system, the kernel would intercept that call, and then it would try to verify that whether that executable can be trusted or not. So this is where the software release process of the enterprise or the software the product vendor comes in, where every software that can potentially run on the system is actually like digitally signed by the software supplier, right? So in this case, pretty much all the binaries, all the executables, or the shared libraries, any kind of scripts or interpreted code, anything that can potentially be executed on the system, that needs to be digitally signed by the software vendor. And in this case, like if the attacker has installed their own malicious software on that system, before that software even is permitted to execute, the kernel intercepts and blocks that executable malicious code from executing on that system. So that is another layer of defense we can use to defend against the software supply chain, hardware supply chain attacks. And another form of like defense we can use is the shell lockout. The whole premise of like attacking the operating system or planting some like malicious software on the system is for the attacker to gain access to the system, because they're able to use the default login to gain access to the shell and either replace the software completely or plant some malicious software, right? So if the shell itself is locked out, we can actually prevent any kind of software from getting installed. And one of the other type of attack surface is the side channel attacks, right? So if the system has been sufficiently hardened with secure boot and verified execution, and the shell has been locked out, with these kind of hardening steps, it'll be very difficult for the attacker to attack these kind of like defense mechanisms. So in that case, they may actually try to use like a side channel attacks where they're actually snooping, various types of like processing that's going on within other processes, and try to predict branching or like other types of like snooping of the memory, and trying to like get the information about those kind of like process level, memory level like data. So for defending against these like side channel attacks, we can use address space layout randomization. So this can be done both at the application layer and at the kernel layer. We can also harden the executable while linking, where we can actually like make sure that the stack is actually non-executable, and we can like enforce that the linker implements stack canaries, where upon return from any function that's being executed within the code, they're actually stack cookies that are set before the code enters a function, and at the time of return from the function, we ensure that the cookies that were set on the stack, they are not tampered with, so that we're not subject to any kind of like heap sprays or memory corruptions that may potentially like lead to attack from side channel attacks. So these are all the defense mechanisms that we can use to prevent against hardware supply chain attacks. Now we'll look at software supply chain attacks. Here, the attacker is actually trying to compromise the software delivery process, where there's a software supplier, and the customer is actually getting the software from the software supplier. When the attacker is targeting a specific customer, right? So what they could potentially do is that they can masquerade, as the software, like hosting the software within their environment, and they pretend to be like delivering software image that is provided by the actual vendor, but indeed what they have done is they have actually like embedded their own malicious software within the original software that was provided by the vendor, right? In this case, if the customer doesn't have a mechanism to verify that the software is actually like trusted, then if they download the software from a malicious website instead of from the actual vendor, then potentially that software when installed contains malicious code in it, and that can be leveraged by the attacker. The other type of attacks that the attacker can do is they can actually attack the vendor itself, right? So the vendor can actually like have a build process. If they have compromised the vendor's network, they can actually like inject their software into the software directly, or if they've compromised the build infrastructure, they can actually like leverage the vendor's build infrastructure to build their own malicious code and deliver the software via the vendor's regular software delivery process. So this is a more advanced type of attacks we have seen, like in the case of SolarWinds, for example, where the attackers have penetrated SolarWinds network and used the SolarWinds software delivery model to deliver their own malware to potentially all of the customers that SolarWinds had at the time, right? So to defend against software supply chain attacks, the first layer of defense would be to enforce digitally signed software. So all of the software that the software supplier ever provides to any customer, right, that need to be digitally signed using X.509 certificates and such. And this doesn't apply to just any one piece of software, but to pretty much like any software installers or upgraders, any kind of software security updates, any sort of software images, whether it be like OS images or virtual images or container images, everything needs to be signed and provided by the supplier. And the second part of it is that when the customer actually downloads or installs the software, they need to digitally verify that these digitally signed software are indeed from the authentic, and they're actually downloaded from the manufacturer's website itself, right? There's another layer of like attacks, as I mentioned earlier, where the attacker would potentially try and compromise the vendor's IT infrastructure, to compromise the software delivery process. So to defend against those kind of attacks, the software supplier should use certificate revocation lists, so that if a certificate was found to be compromised, they can instantly like revoke the certificate. And the software downloaders and installers should check the CRLs and use OCSPs to check the certificate status, to ensure that the certificate that is used to sign the software is still indeed valid and hasn't been compromised. The additional layer of hardening is to use certificate pinning. So there is a tendency for many software vendors to actually get code signing certificates from the public certificate authorities. So the issue with that was that anyone can get a code signing certificate from like the public CAs, right? And if the public CAs are actually being trusted for the digital signatures, then there's still a possibility that software supplier A and a software supplier B can get code signing certificates from the same public CA, and there's no way to verify whether the software supplier B is legitimate, like software supplier or a malicious actor. So certificate pinning is really important, so that each software vendor provide their own certificate pinning. That is actually a dedicated certificate with a dedicated certificate authority to sign their software. The additional layer of hardening to use is the hardware security module, where if the keys and certificates are being managed using a PKI system, where these keys and certificates are hosted on virtual machines or any servers, they may be prone to compromise. But if the keys are actually managed within the hardware security module, the keys are never leaving the device. So that will be like a hardened PKI infrastructure to defeat. And even with all these kind of additional layers of defenses, if the attackers were able to compromise the vendor's network and get their hands on the HSM, then they got the keys to the kingdom. Then they can still get their malicious code signed by the HSM, and they can still deliver malicious code through the software suppliers software delivery model. So in this case, what can be used as an air gap network, where any kind of build infrastructure that is used to sign or digitally sign the software needs to be in a separate segment of network by itself, which is not remotely accessible by the attackers, right? So that is kind of what can help mitigate those kind of attacks. And another way to inject malicious code into the software that a vendor provides is by leveraging any kind of SDKs that are open source or closed source that are actually used but within the software build cycle, right? So because if you consider any modern software, these software are built with well-known open source components, or these software supplier will partner with other companies to get their own proprietary SDKs to build software with it. So if the software vendors' defenses are actually very airtight, and it doesn't allow the attacker to go compromise those networks, the attackers may try to see what other open source software is embedded within that Windows software, or what other SDKs are being used, and they may actually go and try to inject their malicious software into the open source SDKs that they're using, or the proprietary SDKs that they're using. So if the open source software is not thoroughly reviewed during the actual selection and build process, or if the SDKs from any partners were not actually reviewed thoroughly from security perspective, that could be a potential attack surface. So this is another layer of hardening that software suppliers should use to actually prevent against any kind of software supply chain attacks. So now we're going to discuss a little bit more into the vulnerability management, where the vulnerabilities have been around for quite a long time because of the way in which we use and deploy technology products within our infrastructure. And these vulnerabilities are actually software defects or hardware defects that affect a certain product that may not be known at the time of shipping, or they are discovered after the fact, or even if like that vulnerability did not exist at the time of like deployment, due to the advances in technology and more compute and more compute power resources being available, they kind of overpower the security capabilities of any product. And because of that, these vulnerabilities may be exploited for malicious purposes. And that's what has been known to the industry for quite a long time. And these vulnerabilities could be at the hardware layer, or they could be at the kernel. They may affect the operating system. Some of these vulnerabilities are in the runtimes, whether they be hypervisor, container, or any interpreter runtime. And some of these applications may indeed affect the application itself, that is running on top of this various runtimes or operating systems, right? So to address these vulnerabilities, over the past, what the security community has to deal with is to apply, patches that fix these vulnerabilities. These patches may apply to the kernel, they may apply to the operating system, depending on which part of the software stack the vulnerability applies to. The patching needs to be done, and also like the patch, depending on the patch, whether it's a kernel patch or application patch. Systems in production, when we consider patching them, we need to account for the downtime that is associated. We need to account for the maintenance window. We need to go through a lot of like testing and certification cycles, so that when we apply the patch, it doesn't cause any disruption to the production system. So the patching cycle, it's also quite complex and time consuming. Additionally, like the IDS IPS would actually provide some layer of protection, like if in case the vulnerabilities are known, but there's no patch available for that particular vulnerability, to actually remediate or harden against those kind of vulnerabilities, we can deploy IDS IPS to prevent any kind of remote exploitation of these vulnerabilities. Okay, so now we're going to cover how SASE can be used for better vulnerability management. SASE is defined as a secure access services edge. It's a collection of both network and security functions that are deployed in a unique architecture way that can provide a comprehensive like security posture, and at the same time providing better network performance characteristics. So one of the key components of the SASE architecture is a secure SD-WAN architecture, which provides a mechanism for better vulnerability management. So here, any kind of like software-defined solution, whether it be software-defined networking or software-defined element, provides a clean separation of control plane versus data plane, where through the control plane, we actually are able to configure or provide configuration and policies and such. And the data plane element, consumes that configuration and enforces those configuration and policies on the network as the traffic is traversing through them. So with secure SD-WAN, it's kind of like a three-dimensional like solution where there's yet another layer of separation between management. So we have a management plane, control plane, and data plane, and then this actually like provides a layer of cover over the assets. Where in the asset plane you have real infrastructure elements like servers, applications, virtual machines, any kind of like databases, endpoints, all of that is in the assets within a given IT infrastructure. And all of these assets are actually communicating over the network. And all of that network communication goes through a data plane. And the data plane is actually enforcing network and security policies on top of this communication that's going on between the various assets, right? And the type of like configuration and policies that is enforced on the data plane is actually like configured on the management plane. And from the management plane, we actually communicate all of those configured policies through the control plane, right? So this is kind of like a very unique architecture that's only available in a unified SASE, where like there are actually like SASE architectures that's actually a collection of like different types of products and solutions from different disjoint components, that doesn't gel very well. But if we consider like a unified SASE architecture where all of these functions are actually built in and integrated into a single stack, that is enforceable at the data plane, then it'll be like much more easier to manage this from a vulnerability perspective, because then what we would have is like a unique vantage point from the data plane where we have a built-in IDS IPS for any assets that are in the asset plane that for which the patches have not been applied. The IDS IPS automatically protects them from any kind of like remote exploitation, provided that the IPS is actually like updated with the latest signatures. And depending on the testing and certification cycle and the maintenance windows, these assets in the asset plane can be like patched at any time. So that is one benefit of the secure SD-WAN architecture. And we will cover some of these other tools in the tool chest that are a part of the SASE portfolio, especially when we consider zero trust network access. So the reason why zero trust network access is very important is that the perimeter as we know it, the traditional like security perimeter where we have a trusted network and we have like a perimeter in front of it. Everything behind the perimeter is trusted, and everything outside the perimeter is untrusted. That notion of like perimeter is like no longer exists because of the distributed nature of all these like infrastructure moving to either public cloud or private cloud, and all of the devices that are being used to access the corporate resources like applications, data, and systems, they are no longer enterprise managed, right? So in a distributed environment like this, the zero trust network access principles ensures that the devices and the users that access these resources are fully authenticated, and they're fully vetted out from a security perspective and a security posture perspective. And the location from which the access is being made is also factored into the access model, right? So typically if you consider any kind of like vulnerability assessment in the past, they all start with a network probe. They start with a reconnaissance attack, and typically they start out with a IP scan or a port scan or a combination of it to see what assets are available on this network, to be able to like launch attacks, right? So with the zero trust network access, when an IP scan or port scan is run by any attack tool, we don't give anything, right? Because none of the attack tools are actually allowed, because the devices and the user authentication is not performed on those attack tools. So we'll not give anything in terms of the network map, in terms of what IP addresses or ports are live on that network, right? So any kind of reconnaissance attacks are actually moot at this point when we enforce zero trust network access. So now you could actually like think about this other case where, okay, so if if none of the network information is available, without authentication, the attacker may try to compromise the network using stolen devices or stolen credentials, and then try to like probe the network and see like what resources are available for exploitation, right? So for that attack surface, we can use network obfuscation. So what happens is that let's say like a compromised device is trying to do an IP scan or port scan, still we don't give away anything, because we obfuscate the applications and the resources away from the user. So when the user tries to like access a resource, we kind of provide a private IP address, that is not the actual IP address of the application, right? So and then when the user tries to communicate with that particular IP address to reach that application, we reach behind, we look at the policies for that zero trust network access, and only if that access is allowed, then we actually like connect to the application and bridge the two connections. So that way, like the network is totally obfuscated from the user. So the user is actually kind of blindsided, like from what kind of like resources are available for attack within a given environment. So this is a very good strategy to use to defend against these kind of like reconnaissance attacks. So if provided that the attacker doesn't know what kind of applications or what kind of vulnerabilities exist within those applications, they may potentially try to do a brute force attack, like a denial of service attack on the infrastructure. So when we go with a SASE architecture, the DDoS protection is actually built into this fabric. So like any kind of DDoS attacks that are launched, they're automatically mitigated by the SASE architecture. So the applications of the enterprise are automatically protected from any kind of distributed denial of service attacks. Then the next layer of attack surface that opens up is that the attacker would then need to do a more targeted attack where they authenticate their device, authenticate the user, and they know the specific application they're trying to attack. And then within that application, they will try to find any type of vulnerabilities that are known, and those can be remotely exploitable, right? So in that case, IDS IPS is a built-in feature of the SASE architecture. So we can turn on the IDS IPS feature to and then keep updating the IPS with the signatures for the 0-day vulnerabilities or any kind of vulnerabilities that potentially apply for that particular application. So even if the application is not patched with all the security updates, still as long as the IDS IPS gets the latest signature updates for all the 0-day vulnerabilities, we automatically protect these applications from any kind of remote exploitation. Okay. We also have in the SASE portfolio remote browser isolation. This is also a relatively new technology. So far we have been addressing the vulnerability management for vulnerabilities that affect the infrastructure, the systems, the applications, and how to protect them, right? But then there's the other side of the equation where an endpoint is used, software is used, and most of the time these are like a browser is used to access these applications. So if the attacker was able to compromise the user's browser, by leveraging any of the browser vulnerabilities, then they may potentially leverage those vulnerabilities to launch attacks. So in this case, we can use remote browser isolation, where the browser the browser running on the endpoint doesn't actually access the destination website. Instead, we spin up a virtual browser in the SASE architecture, where the virtual browser connects to the remote website and then renders all of the website on the web page, and thereby we actually remove all of the active content on that web page, and we render inactive content to the endpoint browser, where the endpoint browser is not executing any code whatsoever, but it still renders the web page for the user and allows them to interact with that website. So thereby we eliminate all of the browser vulnerabilities by going through the remote browser. And other types of web-based attacks are possible with web applications that are specifically crafted, like OWASP top 10. So these kind of attacks can be protected using a web application firewall. And if the application is also exposing some kind of APIs, then we can actually use web application API protection module to protect those APIs. Okay, so now we have covering the credential theft, right? So as we discussed earlier with zero trust network access, we actually protecting the infrastructure from any kind of reconnaissance or denial of service attacks. Without the user or the device or the location, we're not going to give away anything. So the attackers would then try to steal credentials of the user and potentially use those credentials to compromise and launch more attacks. So we are going to discuss some of the popular techniques that attackers use to steal credentials. They may launch phishing attacks. They may launch social engineering attacks. Some brute force attacks. Brute force attacks are less popular because they're pretty blatant, and they can be caught by security defense mechanisms like IDS, IPS, and so on. So brute force attacks are more popular on the internal networks than on the outside, because what attackers are aware of is that the perimeter defenses are strong, but once they get into the east-west traffic, there's not a whole lot of security infrastructure there. So they're more open to launching like brute force attacks once they have got a foothold within the internal infrastructure. Sometimes they actually like inject like their own like software, like ransomware or trojans that silently like snoop for credentials, and then they can actually like install keyloggers that intercept like record all the keystrokes from the user and remotely phone home to the attacker. Or they can use lateral movement, right, where once they infect one machine, then they can probe the network, they can listen to the network and map out how the network is, and try to move laterally within the enterprise to infect other systems like ransomware does. And they could also be man-in-the-middle attacks and man-in-the-browser attacks, where if you consider like a user going to and connect to a public Wi-Fi network or any public internet access, which doesn't have add a whole layer of security, there might be a case where an unsuspecting user may go through a proxy, and the proxy kind of records all the sessions, and they snoop all of the data that's going through the user sessions, and that is one mechanism in which their credentials can be stolen. In some cases, the browser itself can be compromised, so the man-in-the-browser attacks can actually like try to leverage browser-based vulnerabilities and try to snoop traffic that is going out of the browser to steal like authentication cookies or even like saved passwords, right? So these are all the different ways that the credentials can be stolen, and they can then be used to like defeat the defenses of an enterprise, because with a zero trust network access, we triangulate the device, user, and location, and based on that we enforce policies. Now, if any of these credentials are actually like compromised, then they can actually then be used to launch more sophisticated attacks. So within the SASE portfolio, we have a number of different security functions that can be used to defend against like credential theft. For phishing and social engineering attacks, we have the next-gen firewall, we have the secure web gateway, we have remote browser isolation, cloud access security broker, and on top of it, we'll have multi-factor authentication. So when a user clicks on a phishing email, the link that comes via phishing email, instead of like allowing the user's browser to render that content, if we like direct that request to a remote browser, right? So then we can actually show that page in preview mode where the user is not allowed to interact with it. So let's say if a user gets an email saying your Office 365 password has been compromised, click here to reset. And if the user clicks on that, they go to a virtual browser, which actually like makes that page to be preview only mode, and they cannot interact with it. We can actually prevent a lot of those kind of phishing attacks. Similarly, like next-gen firewall, secure web gateway, they all provide a lot of like defense mechanisms to prevent against like phishing and social engineering attacks. There's also these brute force attacks and credential harvesting, keyloggers, and lateral movement. So all these types of attacks can be prevented using next-gen firewall, IDS IPS, antivirus, and advanced threat protection. We also have man-in-the-middle and man-in-the-browser attacks. For these as well, we can use next-gen firewall, secure web gateway, web application firewall, and API protection. We can enforce multi-factor authentication. So depending on the baseline behavior of a particular device or a particular user, we can actually like if there's any outlier connection that comes from that particular device, then we can actually potentially like enforce multi-factor authentication to reinforce step-up authentication in addition to like the default authentication. So these are all like techniques that we can use to defend against credential attacks, credential theft attacks. So we then go into ransomware attacks. So ransomware attacks we have seen, have been like quite popular across multiple industry verticals. And not only are the attacks getting more sophisticated, but the stakes are actually only going higher. So recently, like at an industry conference, we actually like learned that the amount of money involved in like ransomware attacks and the actual like cybersecurity incidents is actually gone up quite significantly into like multiple trillions of dollars. So that's actually like pretty astounding, because they are almost reaching the size of a country's GDP. So there's more organized attacks that and more sophisticated attacks, and these attacks are like not happening like within a short amount of time. Typically, they are happening more over a longer period of time, where from the time of initial infection to the time where the attacker is able to encrypt a lot of like different systems in a given network. It takes several months to even like more than a year, right? So some of the like attack techniques that the attackers use to get a foothold in a particular enterprise and then spread laterally within the enterprise, target high value systems, and target high value data that is very critical to the operations of a particular enterprise, and then try to encrypt it and hold the data ransom to their own like advantage. And then once they get a hostage of the data, and they try to encrypt all the data, and then make deny the user from accessing that data, then they demand ransom, and only if that organization pays the ransom that they have demanded, then they will actually offer to decrypt the data and make the data available to that enterprise. So this has infected not only like several customers in different sectors like financial sector, healthcare, oil pipeline, and all these different types of sectors, but they have also like affected like even federal governments, like state governments and other organizations, and it's been pretty significant problem that needs to be addressed. So now we're going to look at some of the tools we have in the SASE portfolio that can be used to defend against ransomware attacks. So here we have various types of like tools, traditional like firewalling, next-gen firewalling, secure web gateway, cloud access security broker, which also offer various kinds of like filtering mechanisms at the IP, DNS, URL layer, and we have more content inspection based tools like file filtering, IDS, IPS. We have antivirus, sandboxing for like zero-day malware that perform like various kinds of like behavior analysis, and advanced threats can be detected such way. Remote browser isolation is also like gaining a lot of popularity in defending against these kind of drive-by downloads or phishing attacks, where the initial like attack that happens in kind of a ransomware is there's a very lightweight malware installed on the system that appears to be benign and escapes the radar of like any behavior-based system like a sandbox analysis. But then at some point later in time, at a random place in time, this initial malware that's been downloaded will try to download the actual payload that is more dangerous, right? So to prevent the initial infection from happening, remote browser isolation can be effectively used, because spear phishing is the most like popular type of attack to initially cause that initial infection to any device. Okay, so these are some of the tools available. And so, the way to utilize or deploy these tools from within the SASE portfolio to protect against these ransomware protection is typically we have the internal network. You can use the next generation firewall to deeply segment the internal network, and each network segment is actually like protected by its own next-gen firewall that defends like against lateral movement detection. I mean, it defends lateral movement and protects the lateral movement of any ransomware. And as the traffic like goes out to the public internet, whether it be like private cloud or public cloud or any kind of like internet-based websites, there's an additional layer of like cloud-based gateways that actually like protect, based on, IP, URL, DNS filtering, based on reputation. And there's more like content-based inspection tools like IDS, IPS, file filtering, antivirus, sandboxing, and RBI can be used at the perimeter layer, so that the ransomware can be like detected and blocked effectively at the perimeter. But then once the the attacks cross over, like and maybe like the device connected to some untrusted network and got infected. And if the infection tries to spread laterally from that particular machine to like some other machines within the network, then we are able to then again detect that lateral movement and block it with the internal segmentation that we can achieve with the next generation firewall. Also, there's been like a lot of open source software around ransomware. So there's now open source ransomware kits that you can download and deploy within the network, and then sort of like test your defenses against like ransomware, where you can actually simulate a ransomware attack and sort of test your like security defense posture to see if the initial infection is actually like detected and prevented effectively. And in some cases, like you can simulate an attack where if the initial infection was indeed successful, and if that device tries to probe others machines in the network and tries to spread laterally, are the security defense mechanisms able to detect that lateral movement? So you can actually like run periodic tests within the environment to ensure that the security defense posture is actually like continually monitored and tested and ensure that that it is effective against these ransomware attacks. Okay. So the last type of like attacks, modern attacks, we're going to consider in this presentation is the 5G and IoT based attacks. So here, when you consider 5G, it brings a lot of promise to the network speeds. So 5G promises that it will try to decrease latency by 10x. It would increase the connection density by 10x. There's almost like a 10x increase in like throughput, and there's a 100 times reduction in the energy utilization, and 100x more traffic capacity. So that means that there's a higher scale of like and higher throughput networks with a higher high capacity and high density networks. Now these networks can be like used to build very good applications with considering like we can actually like leverage that network capacity for real-time communication between the various like endpoints that use them. But at the same time, these high-speed networks can also be like misused or abused by malware or attackers. So case in point being the IoT devices, for which the 5G networks are very suitable for, where these IoT devices are in the millions, or not, if not in the tens of millions, and the number of different types of IoT devices in the future is only expected to grow exponentially. These are very low-powered devices, and they have not been built with security in mind. They're all connected to these 5G networks. And now, because of a vulnerability that exists within these IoT devices, attackers can remotely exploit these IoT devices and then use them for nefarious purposes. So some of these, like security attacks, we have already seen in the past. That what kind of attacks are possible with these IoT devices. I'll give you two examples. One example is casino attack in Las Vegas, where in a casino there was a fish tank and there was a thermometer installed on the fish tank to monitor the temperature of the fish tank. So some smart attacker figured out that that thermometer was a smart IoT device, is a smart device, and they actually queried, researched about the manufacturer of that smart thermometer, and they researched like what stack it's running and what vulnerabilities applied to that thermometer. They hacked into the thermometer. Now, once they got into that system, they realized that that particular thermometer is not properly segmented from other parts of the network. So, of course, they were able to move laterally within the network to other systems, and they were actually able to, hack into the casino's financial database, right? So, so this is actually quite a real threat because not only are these IoT devices not researched from a security perspective, because due to the sheer volume of these different types of IoT devices, it will be very hard to actually research them for security and analyze them for vulnerabilities and patch them. But at the same time, for attackers looking for specific targeted threats, they can actually compromise a certain device, and then once they get a foothold of the system, they can spread laterally and attack other parts of the system that are high value targeted, potentially more lucrative targets. The other type of the second example I would like to mention here is the IoT cameras, right? So there was actually like an attacker who compromised a whole bunch of like security cameras that were deployed within an enterprise. And these cameras have very low powered compute device, right? So, but then still they were, the attacker was not able to move laterally, but instead what they did was, they harnessed the compute power that was available on these like cameras to launch a denial of service attack on a specific target. And the scale of that attack was like pretty significant because that was a 300 gigabits per second denial of service attack, which is one of the very large, attack by volumetric DDoS attack, to date, right? And considering that this is a low-powered IoT camera, that was used, they just like used a whole bunch of those cameras to launch that kind of attack. Another technology that the 5G, brings to bear, as service providers roll out these 5G networks, is they bring a new technology called mobile edge compute, which is actually like a compute resource on which a workload can be run at the edge of the network, and that actually, if that is compromised and it's taken over by the attackers, just with the compute power that's available on an IoT device, they were able to launch like a 300 gigabits per second denial of service attack. But imagine if the mobile edge compute, which has a whole lot more processing power, if that was compromised, you can imagine the scale of the denial of service attack that attacker could launch by compromising those mobile edge compute kind of resource. So now we can look at how SASE architecture can actually provide holistic security in the end-to-end spectrum of a 5G network. So the SASE orchestration platform can be used to deploy security appliances, whether they be physical or virtual, at various parts of the 5G network. It can be we can deploy the security stack at the radio access layer, right? Where the IoT devices are actually communicating directly over the radio network, to the edge of the network. Right there, we can actually have a layer of security. We can also deploy security at the mobile edge compute, where there's edge compute workloads that can be run. We can also run deploy security at the aggregation points from the radio networks, and we can actually deploy security at the edge of the network, where this traffic eventually makes its way through and finally accesses the public internet or any kind of cloud resource. So the deployment, provisioning, configuration, so all of this becomes like super easy because there's a single pane of glass to manage, and any kind of security attack that happens anywhere within the edge of the network or the radio network or the core network, we provide full visibility into what exactly happened in the entire tool chain. And we also discussed like one scenario where in the current enterprise networks, the underlaid transport mechanisms that are available today are the MPLS, the broadband internet, the 5G, 4G LTE networks. So in addition to this, like we also have the 5G access layer. So with the built-in SD-WAN capability, we can leverage the 5G as another layer of transport, and we can provide like the right mix of performance and SLA characteristics of the network, along with integrated security, layered in on top of these like different transport mechanisms, regardless of the underlying transport. This provides like a very future-proof design from an enterprise perspective, where the 5G layer doesn't bring like an additional attack surface, but with the built-in security, we are actually like addressing that attack surface with added security. So hope this keynote was very helpful. We covered a wide range of modern attacks that we have seen in the last 5 years, And the new SASE architecture that is actually being deployed as we speak, it holds a lot of like arsenal in the tool chest to defend against all these kind of like different modern attacks. We provide like advanced strategies that can be used to defend these kind of attacks. Thanks everyone for joining. Back to you, Mike.